Okay, so we'll start now. In last lecture, we have seen electrical analogy of radiation. Similar to electrical analogy of conduction, there is electrical analogy of radiation. What is the meaning of word analogy? The word analogy means similarity. Electrical analogy of radiation means the similarity of electrical circuits with thermal circuits, which are involving radiation heat transfer. Now, in case of electrical circuits, we consider three things. One is voltage, that is driving potential, one is current, and one is electrical resistance. Right? Now, in case of thermal circuits, in case of radiation, the driving potential is sigma into bracket T1 raised to 4 minus T2 raised to 4, where sigma is the Stefan Boltzmann's constant. I repeat, in case of thermal circuits involving radiation, the driving potential is given by the formula sigma into bracket T1 raised to 4 minus T2 raised to 4. Now, in case of thermal circuits involving radiation, there are two resistances. Which are those? One is surface resistance and one is shape resistance. Now we'll discuss what is surface resistance, why it is called as surface resistance, and why shape resistance is called as shape resistance. Because surface resistance is offered because of the surface, right? It is the resistance offered to the flow of heat by radiation at the surface itself. It may be the resistance offered to emission of energy, or it may be the resistance offered to absorption of energy, right? And the next resistance is shape resistance. What is shape resistance? The resistance offered due to because of geometry, shape and orientation, that is called as shape resistance. In last lecture, I have given you one example. Let's say I have prepared 10 concepts for the session, right? And I have to deliver it to you. So I may not be able to explain all 10 concepts in a very lucid language, right? So there is some resistance. I'm having some resistance, right? So out of 10, I will be able to explain only 9 concepts to you. So that is my surface resistance. Now see, you are listening through this internet. So you might be having some range issue. Some issues will be there. You may be having some clarity issues. You may not be able to hear properly. So this resistance is called as shape resistance, right? It is due to geometry, shape and orientation. So maybe 9 concepts I have delivered very nicely, but out of those 9 concepts, you were able to hear only 7 concepts properly. So that is shape resistance. Now you have heard 7 concepts, but you have not understood 7 concepts. That just they have reached your ears, right? But you have not understood that. So why it may, there may be some many reasons, like you may not have attended previous session, or you some of the prerequisites, some of the basics may not be clear to you. So that is your surface resistance. So 3 resistances were there. First was my surface resistance, second was the shape resistance, and third was the student surface resistance. So in case of electrical circuits, there are 3 resistances. One is surface resistance and one is shape resistance. As I told you, surface resistance is 1 minus emissivity upon area into emissivity. Now, we have discussed what is emissivity. Emissivity is the ratio of emissive power of a surface to emissive power of a perfectly black surface. Now let's say consider example of a black surface. So what will be surface resistance of a black surface? The emissivity of the black surface is 1. So 1 minus emissivity, 1 minus 1, it will be 0. So surface resistance offered by black surface will be always 0. But we know that in our day-to-day life, no surface is having emissivity as perfectly 1. Perfectly black body is a hypothetical concept, right? Okay. So surface resistance is given by the formula 1 minus emissivity upon area into emissivity. It is the resistance offered at the surface to the emission of radiant energy or to the absorption of radiant energy. Okay. I believe that it is clear to you. Now shape resistance. As I told you that shape resistance is offered due to geometry, shape and orientation of the objects, right? Between which the radiant heat exchange is occurring. Shape resistance is given by the formula 1 upon A into view factor, 1 upon A1 F12. See these two simple formulas, and based on these two simple formulas, you can work out any numerical of this unit. Now in radiation, there are two parts. One part is exclusively electrical analogy of radiation, which is very important. because being an engineer, we will have to work out with this dimension. Now, this is comparison of electrical circuit and this equivalent resistance. Already we have discussed this, that surface resistance is given by the formula 1 minus emissivity upon area into emissivity, and shape resistance is given by the formula 1 upon A into F12. Now, driving potential is sigma into T1 raised to 4 minus T2 raised to 4. Let us take a very simple example. The first case, heat transfer between two infinite parallel plates. Now these are the two plates. One is having temperature T1, emissivity epsilon 1. The second is having temperature T2, emissivity epsilon 2. Now we have to work out how much heat is flowing by radiation from plate 1 to plate 2. Now, when heat will flow from plate 1 to plate 2, it will be subjected to that radiant energy, that radiant heat energy will be subjected to three resistances. Which are those? One is surface resistance of plate 1. Second is R2, shape resistance of plate 1 with respect to 2. And next, surface resistance of plate 2. R1, R2 and R3. Now, as we know, just now we have discussed that the surface resistance is 1 minus emissivity upon area into emissivity. 1 minus epsilon 1 upon A1 epsilon 1. This will be value of R1. What will be value of R3? What is R3? Surface resistance of plate 2. So emissivity of plate 2 is epsilon 2. Area of plate 2 is A2. So what will be value of R3? It will be 1 minus epsilon 2 upon A2 epsilon 2. See, this will be value of R1, 1 minus epsilon 1 upon A1 epsilon 1. What will be value of R2? 1 minus epsilon 2 upon A2 epsilon 2. And what is second resistance? Shape resistance of plate 1 with respect to 2. I call it as R2. So it is 1 upon A1 F12. What is F12? View factor of 1 with respect to 2. Fraction of energy emitted by 1 which is intercepted by 2. I believe that these three formulas are clear to you. And if these three formulas are clear to you, this derivation is very simple. In some of the exams, this derivation has been asked for 8 marks. Derive an expression for heat transfer by radiation between two parallel infinite plates. Now see, derivation is very simple. In case of electrical circuits, we write Ohm's law. I is equal to V upon R. Current is equal to potential upon resistance. Similarly, in electrical circuits, we can write, now see, there is current in electrical circuits. Similarly, in thermal circuits, we write Q. Q is nothing but heat transfer rate. So Q is equal to driving potential is sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by thermal resistances. They are R1, R2 and R3. So in this case, I will write QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by R1 plus R2 plus R3. So this simple 2 or 3 steps derivation is there which has been asked for 8 marks. So QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by summation R. And how many resistances are there in this case? There are 3 resistances. Surface resistance of plate 1, shape resistance of plate 1 with respect to plate 2, and third is surface resistance of plate 2. So QR will be equal to this sigma into bracket T1 raised to 4 minus T2 raised to 4. Simply I have substituted the values of R1, R2 and R3. I believe that the screen is visible to you. You are able to see this. Now see, we will make one more substitution. What is that substitution? As the plates are infinite, we can say that their areas are same. So we can say that A1 is equal to A2 is equal to A, and as the plates are infinite and as the plates are parallel, all energy emitted by 1 will be intercepted by 2. So view factor or shape factor of 1 with respect to 2 will be equal to 1. So if you substitute those values, now A I have taken common because A1 and A2, they are same. In first term, A1 was there, in second term, A1 was there, in third term, A2 was there. So simply I have substituted A1 is equal to A2 is equal to A. And that A I have taken outside the bracket. So it is 1 upon A. Okay. Okay, so this A will go into numerator. Then I will substitute the value of F12. The value of F12 is 1. And if I substitute F12 is equal to 1, this minus 1 plus 1, it will get cancelled. And finally, I will get in the denominator 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. So what equation I will get for a radiant flux? Which equation I will get for radiant flux? I will get the equation QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Now, if I want to find how much radiant flux is flowing between two infinite parallel plates, I will use this formula. QR is what I want to find. I want to find radiant flux, means area will be 1 meter square, right? Sigma is Stefan Boltzmann's constant. Its value is 5.67 into 10 raised to minus 8. T1 and T2 are absolute temperatures of plate 1 and plate 2. Absolute means temperatures in Kelvin, right? And epsilon 1 and epsilon 2 are emissivities of plate 1 and 2. So if I know the temperature of both plates, if I know the emissivity of both plates, I can work out how much heat is flowing by radiation between two plates. Okay, is it clear to you? Okay, so I believe that it is clear to you. Simple expression, radiant flux is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Now, in numericals are very easy, just one step, plug in, plug out kind of stuff. Put the values, get the answers. In numerical, you will be known what is epsilon 1, what is epsilon 2, what is T1, what is T2. Right? So if you know the values of T1, T2, epsilon 1, epsilon 2, you know that sigma is constant, you know its value, just put the values and get the answer. In last lecture, we have worked out this numerical. I will just read out this numerical for you. I will just take your 2 minutes. Two large plates of emissivity 0.1 and 0.05. So epsilon 1 and epsilon 2 is given. Their absolute temperatures are given. So T1 is 350 Kelvin and T2 is 300 Kelvin. The distance between the two plates is given, but it is not our cup of tea. We are not interested in how much is the distance, because what we require simply the values of T1, T2, epsilon 1, epsilon 2. What we have to find? We have to find how much heat transferred by radiation per unit area. So we have to find radiant flux. So which formula we'll use? Simply we'll use this formula. QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. And if you put the values, you'll get this value of radiant flux, which is 13.5 watts per meter square. We are not interested in the values, but we are interested in the concept. So simply, if temperature and emissivities are known to us, we can work out the radiant flux. I believe that it is clear to you. Now we'll move on to the next part. Now see, in practical cases, let's take example of a furnace, right? In that case, we have to minimize the radiation heat losses. So for that purpose, we will use radiation sheet, right? We'll use radiation shields. They are very thin shields or thin films having very low value of emissivity. What is the objective behind providing radiant shields? The objective behind providing radiation shield is to minimize the heat transfer by radiation. Now, they should have low emissivity, that is obvious. Now see, if there, can I use a black surface as a radiation shield? Obviously no, because if I use a black surface as a radiation shield, it will absorb all, right? It will not have any surface resistance. Okay, I think that you are understanding this. It will reduce the radiation heat transfer in furnaces, combustion chambers. We use this exclusively in X-rays, right? You might be knowing that X-rays, their wavelengths are extremely small. Now, if wavelength is very small, frequency is very high, E is equal to h nu. So they are carrying extremely high energy. The photon energy is very high. So to mitigate those external radiations in case of nuclear reactors as well as X-ray machines, we use radiation shields. Okay, now we'll work out a numerical which is best. I believe in last lecture we have worked out this also, this derivation as well as one numerical. Within 2 minutes, we'll just revise. Now see, we'll work out the mathematical dimension, how to find heat transfer between two plates when they are separated by a radiation shield. Now let's consider that two plates are there. One plate is 1 and the second plate is 2, right? And a third plate is introduced between the two plates. Let's say that the temperatures of plate 1 and plate 2 are T1 and T2. Emissivities are epsilon 1 and epsilon 2. And the plate, or let's call this plate as radiation shield. The shield which is introduced between two plates 1 and 2 is, let's call it as 3. So T3 is the temperature of the radiation shield. Epsilon 3 is the emissivity of the radiation shield. Now see, if I consider this case, Now, in previous case, only two plates were there. There was no radiation shield in between two plates. So in that case, there will be only three resistances. Now, if a shield is placed in between two plates, how many resistances will be there? There will be six resistances. Which are those? I will just read it out for you. First one is the surface resistance of plate 1. Second is shape resistance of plate 1 with respect to shield. Third is surface resistance of the shield on the left side. Fourth one is surface resistance of the shield on the right side. Fifth one is shape resistance of the shield with respect to plate 2. Sixth one is surface resistance of plate 2. So there will be six resistances. Now, as the plates are infinite, I can say that A1 is equal to A2 is equal to A3. As the plates are infinite, the view factors will be 1 because the plates are infinite and they are kept parallel. What will be driving potential? The first plate is 1. Energy is emitted by 1 and it is reaching up to 2. So we have to calculate exchange between 1 and 2. So what will be driving potential? It will be sigma into bracket T1 raised to 4 minus T2 raised to 4, where T1 and T2 are absolute temperatures. So according to electrical analogy, what equation I can write? I can write the equation Q is equal to driving potential upon resistance. So I can write the equation QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by R1 plus R2 plus R3 plus R4 plus R5 plus R6. Now what is R1? Surface resistance of plate 1. So it is 1 minus emissivity of first surface. We have seen that the formula for surface resistance is 1 minus emissivity upon area into emissivity. What is R2? Shape resistance of plate 1 with respect to plate 3. That is 3 is nothing but shield plate, right? So it is 1 upon A1 F13. What is R3? Surface resistance of plate 3 on the left side. Surface resistance of shield on the left side. So it is 1 minus emissivity upon area into emissivity. In the last lecture, I told you that it may look lengthy, but it is very simple. You have to remember just two very simple formulas. One is surface resistance, which is 1 minus emissivity upon area into emissivity. And second is shape resistance, which is 1 upon area into shape factor, right? Okay. So similarly, this is R4. This is R5. What is R4? Surface resistance of plate 3. It is 1 minus epsilon 3 upon A3 epsilon 3. What is R5? Shape resistance of the shield plate with respect to plate 2. So it is 1 upon A3 into view factor of 3 with respect to 2. I told you it is 1 upon product of area and view factor. Now energy is flowing from 3 to 2. So we have to consider a view factor of 3 with respect to 2. So it is 1 upon A3 into F32. And what is the last resistance? Surface resistance of plate 2. 1 minus epsilon 2 upon A2 epsilon 2. Now, simply you have to substitute these values. The derivations are very simple. Simply you have to substitute QR is equal to driving potential upon resistance. Simply substitute the values of R1 to R6. Substitute the condition that A1 is equal to A2 is equal to A3 is equal to A. So this A will come outside. And after that, make second substitution that the view factors are unity. F13 and F32 are 1. So if you substitute that, this is the final step that you will get. What is the final step that you will get? It is very simple substitution. And once you substitute this, -1 + 1 will get cancelled. So this is the final step that you will get. What is the final equation that we are getting? The equation is QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4, right? Divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. This is similar to previous. Without shield also, we were getting this first bracket. Now, with shield, we are getting this additional bracket. What is the value of that bracket? 2 upon epsilon 3 minus 1. So what is the formula for QR upon A without shield? The formula is sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. And what is the formula with shield? Radiation with shield. It is, we have to add one more term in the denominator, which is 2 upon emissivity of shield minus 1. I believe that it is clear to you. Once it is clear to you, the numericals are damn easy. As I told you, it is just plug in, plug out kind of stuff. Simply see, emissivities of plates will be given to you. Emissivity of plate 1 is epsilon 1. Emissivity of plate 2 is epsilon 2. Temperatures of plates are given. Temperature of first plate is T1. Temperature of second plate is T2. If it is given in Kelvin, keep it in Kelvin. If it is given in degrees Celsius, convert it into Kelvin. And epsilon 3 here is nothing but emissivity of the shield, which is introduced in between, right? Now we have worked out this numerical. In this case, T1 and T2 were given, right? See, find out the heat transfer rate per unit area due to radiation between two infinite long parallel plates. The first plate has emissivity of 0.4. So what is given? Epsilon 1 is given 0.4. It is maintained at 200 degrees Celsius. I cannot take temperatures in Celsius. As I told you, in radiation, we have to take temperature in Kelvin. In radiation, if you take temperatures in degrees Celsius, your answers will go wrong because radiation is governed by Stefan Boltzmann's law, which focuses on absolute temperature, not on temperatures in degrees Celsius. Okay, so we have to convert that temperature into Kelvin. Okay, and the emissivity of second plate, so it is nothing but epsilon 2, that is given. The second plate is maintained at 30 degrees Celsius. 30 degrees Celsius means 303 Kelvin. So T2 is given. Now, emissivity of the shield is given. A radiation shield having emissivity 0.5 is introduced in between. So epsilon 3 is given. You can call it epsilon 3. In some of the reference books, it is called as epsilon S. It depends on you. I call it as epsilon 3. So epsilon 3 is 0.5. What we have to find? We have to find the percentage reduction in heat transfer rate due to radiation shield. How can I find percentage reduction due to radiation shield? For that, I have to work out heat transfer rate without radiation shield and heat transfer rate with radiation shield. Let's say that without radiation shield, the heat transfer rate is 100 watts per meter square. And with radiation shield, the heat transfer rate is 60 watts per meter square. So what I will do, how much is the percentage reduction? It is 40. How I have calculated that 40? 100 minus 60 upon 100. So it is Q without radiation shield. Percentage reduction will be equal to Q without radiation shield minus Q with radiation shield divided by Q without radiation shield. So simply if you substitute that, so now see, this is the given problem. T1 is given, T2 is given, epsilon 1, epsilon 2, epsilon 3 is given, and we have to find percentage reduction. So how I can find? This is a simple formula. This is QR upon A. The upper formula represents heat transfer rate by radiation, right, with radiation shield, and the second formula represents heat transfer rate by radiation without radiation shield. So you will work out this is without and this is with. Without minus with divided by without, that will give you percentage reduction. I believe that it is clear to you. Now next part is very interesting. First part was this. See, being an engineer, why we introduce radiation shield? Because we have to reduce heat losses. So when you will work in industry, the question may be given to you that if we have to reduce this by 100 times, or let's say it is 1000 and we have to reduce it up to 500. So you will design how many shields are required, right? What should be their emissivities? Either emissivities will be known to you, the shields are available, and you are supposed to design how many shields are required. That is number of shields. That is what you will work out, right? Okay. Now in this case, the second part is we have to find temperature of the shield. Now when we will work out temperature of the shield, we'll apply very simple concept that heat flowing from 1 to 3 and heat flowing from 3 to 2 and heat flowing from 1 to 2, they are one and the same because these are in series. If I talk about all resistances, these all resistances are in series, and we know that in series current remains same. So whatever heat is flowing from 1 to 2, same heat is flowing from 1 to 3. So if I draw electrical analogy for 1 to 3, what equation I will write? QR upon A is equal to sigma into bracket T1 raised to 4 minus T3 raised to 4. Yes. What I can write? QR upon A is equal to sigma into bracket T1 raised to 4 minus T3 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 3 minus 1. Is it clear to you? Because in between these two plates, there is no any other plate. So this is the case that no plates are in between. So simply I can use this equation. Now see, QR upon A is already known to me. In the first part of question, I have worked out this QR upon A with shield, right? So same QR upon A will be there. T1 is known to me. Epsilon 1 is known to me. Epsilon 3 is known to me. So I can work out T3. Let's say I want to cross check my answer. We want to check whether whatever calculation we have done, is it right or not? So what you can do, on the similar track, you can find T3. What will be one more option to work out T3? Here we have considered the heat flow rate from 3 to 2. In spite of that, let's say any student says that whatever is the heat which is flowing from 1 to 3, same amount of heat is flowing from 3 to 2. So what equation he will write? he will write the equation QR upon A is equal to sigma into bracket T3 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 3 plus 1 upon epsilon 2 minus 1. And he will get same answer for T3. Okay, I believe that this is clear to you. Now this is next numerical. You need not write it down. I will, after the lecture, I will share this with you. Okay. Now in this case, what is given? This is from university exam. That's why I have specifically highlighted this. Two large plates are there. They are maintained at temperature 600 and 300. So what is given? T1 is given. How much will be T1? 600 plus 273. So it will be 873. How much is T2? 300 degrees Celsius means 300 plus 273. So it will be 573, right? And emissivity is 0.9 and 0.4 respectively. So epsilon 1 is 0.9, epsilon 2 is 0.4. A radiation shield having emissivity of 0.02 is inserted in between them. So epsilon 3 is given as 0.02. What you are supposed to find? Calculate the heat transfer rate without shield. What will be formula for heat transfer rate without shield? The formula will be QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by, in first bracket, 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1 plus in second bracket 2 upon epsilon 3 minus 1, right? Now, what will be heat transfer rate with shield? Whatever formula I have told just now, that is the heat transfer rate with shield, right? What formula you will apply for without shield? That second term will not be there. And how will you find temperature of shield? By the same formula. The concept is similar to this one. Okay, this formula you will use for with shield. The second formula you will use for without shield. And this formula you will use to work out temperature T3. I believe that this concept is clear to you. If it is clear to you, we can proceed to the next numerical. Now in this numerical, what is the difference? This is also numerical of two parallel infinite plates, right? In between the two plates, radiation shield is introduced. Only what is the difference? In previous case, there was only one radiation shield. In this case, there are two radiation shields. Now see, in this case, two long plates A and B, they are maintained at temperature 600 Kelvin and 300 Kelvin. So two plates are there. They are maintained at temperature 600 and 300 Kelvin. Their emissivities are also given. Let's say the plates are A and B. So we will call it as epsilon A and epsilon B. They are given as 0.8 and 0.5. Okay. The two radiation shields C and D having emissivities 0.5 and 0.4 are introduced between the plates such that the plates are in the order A, C, D, B. Now, so what is the order? The heat will flow from A to B, and in between A to B, C and D shields are placed. So the order is A, C, D, B. Okay. Assuming the plates to be infinite long, find the rate of heat exchange per unit area and steady state temperatures attained by plates C and D. Now, this is the arrangement. The first plate is A, the second plate is, or last plate is B. Heat is flowing from A to B, right? Their temperatures are given, 600 and 300. Their emissivities are given, epsilon A and epsilon B. Now, two plates are introduced in between them. Plates C and D. Epsilon C is given, epsilon D is given, right? What we have to find? Heat exchange. Now see, if only C plate was there, what formula we would have used? We would have used the only second bracket, right? Now one more shield is there, no? So we will use one more bracket. And what is the formula over there? 2 upon emissivity of shield minus 1. See, if no shield is there, these two terms will not be there. Concentrate on the denominator. See, QR upon A is equal to sigma into bracket TA raised to 4 minus TB raised to 4 divided by this denominator. Now focus on this denominator. If no shields are there, second and third term will not be there, right? If only one shield is there, only this second term will be there, 2 upon epsilon C minus 1. Now as two shields are there, I have to write two terms. One is 2 upon epsilon C minus 1 and one is 2 upon epsilon D minus 1. Let's say if one more shield is there, so I have to add one more bracket. And what will be that bracket? Let's say E shield is also there. So here in the denominator, I have to write plus into bracket 2 upon epsilon E minus 1. Are you getting? If one more shield is there, let's say F shield is also there. Two more shields are there, E and F. I think E is clear to you. If F shield is there, again I have to write plus 2 upon emissivity of F minus 1. So this simple formula, this only one formula you have to remember. Whenever you will work out numericals from electrical analogy, simply you have to remember this simple formula. QR upon A is equal to this. Is it clear to you? Now see, this is also plug in, plug out kind of stuff. Means just you have to substitute these values and you have to work out the values of QR upon A. If you substitute the values of emissivity of plates A, B, C and D and temperatures of plate A and B, and if you substitute sigma is equal to 5.67 into 10 to the power minus 8, you will get the value of QR upon A. Okay, I believe that it is clear to you. Okay, now we have to find temperatures of plate C and temperature of plate D. How can I find temperature of plate C? For that, I have to consider exchange between A and C. Now for A and C, what equation I can write? QR upon A is equal to sigma into bracket Ta raised to 4 minus Tc raised to 4 divided by 1 upon emissivity of A plus 1 upon emissivity of C minus 1. So if I use that formula, I will get temperature of plate C. Similarly, how can I find temperature of plate D? Yes, how can I find temperature of plate D? I'm having three options. Either I can consider exchange from plate A to D, but there again I have to consider this heat transfer rate with chill, or simply I can consider heat transfer from D to B. If I consider heat transfer from D to B, which expression I can write? I can write the expression QR upon A is equal to sigma into bracket TD raised to 4 minus TB raised to 4 divided by into bracket 1 upon emissivity of plate D plus 1 upon emissivity of plate B minus 1. Is it clear to you? So if you do that, you can work out the value of temperature TD. Tell me honestly, is it clear to you? Any difficulty with this? So in this case, two radiation shields were there, right? So if two shields are there, we have to write two brackets, right? This one first bracket epsilon C, this is for shield C, and the second bracket is for shield D. Okay. So if you are having pen and paper, please write down this numerical, because this numerical is important from GATE and IS perspective. Also in many of the competitive exams, similar kind of numericals will be asked. Okay, so please write it down. Net radiation from two large infinite plates maintained at temperature 73 degrees Celsius and 23 degrees Celsius is to be reduced by 105 times. Now, what is the temperature of plate 1? It is 73 degrees Celsius, right? Okay. If you add 273 and 73, how much you will get? It will be 346. So it is 346 Kelvin is T1. What is T2? T2 is 23 degrees Celsius. So 23 plus 273, it will be 296 Kelvin. It is to be reduced by 105 times. So there is some radiant heat exchange between these two plates, which are maintained at temperatures 346 Kelvin and 296 Kelvin. And what is the target? We have to reduce that radiant heat exchange by 105 times, right? And what we have to calculate? We have to calculate the number of radiant shields to be placed in between them to achieve this effect. And it is given that emissivity of the shield is 0.05. How much is the emissivity of shield? It is 0.05. And it is given that the emissivities of plates are 0.8. Emissivities of both plates are same. Epsilon 1 and epsilon 2 is same, and the value is 0.8. Now, what is the next part of the question? The next part of the question is, after this, if one of the shields is removed, how many times will the net radiation will get reduced? Okay, this we'll discuss later on. Let's say this is also very simple. Let's say that we work out that to reduce the heat transfer by 105 times, 4 shields are required. Then what is given in the next part? If one of the shields is removed. Now, so in this case, if 4 shields are there, if one is removed, there will be 3 shields. So what he is saying that if 3 shields are there, how much is the net reduction in the heat transfer rate? Anyway, we'll work out on the first part. We have to work out number of shields required to be provided so that the heat exchange will get reduced by 105 times. Initially tell me, is the question clear to you? Because we have not worked out this kind of question, that how many number of shields should be there. Okay, now see, T1 is given, T2 is given. Now see, this is the formula which we have to use when we have to calculate number of shields. As I told you, if one shield is there, only one shield is there, only this term will be there. If two shields are there, this bracket again it will get added, no? So simply, instead of writing it again and again, simply I have multiplied this bracket by a term n, where n is the number of shields. If no shields are there, n will be 0. So only this term will be there. And this formula we use. When we use this formula, we use this formula when there is no shield in between the two plates. If n is 1, what will be this formula? It will be 1 upon epsilon a1 plus 1 upon epsilon 2 minus 1 plus 2 upon epsilon s minus 1. When we use this formula, if only one shield is there, we have worked out numerical of that type. If two shields are there and if their emissivities are same, I can take this bracket as common and I can multiply that bracket by n. Tell me honestly, is it clear to you? In this numerical, what is given? The values of temperatures T1 and T2 are given. The values of emissivities epsilon 1 and epsilon 2 are given. Right? And what is given? Which shield? The heat loss which shield should be get reduced by 105 times. So QR upon A. QR is heat transfer rate by radiation. Upon A means we have to find radiant flux. So radiant flux with shield will be equal to radiant flux without shield divided by 105. Now, we can work out radiant flux without shield, no? Simply what will be the formula? Radiant flux without shield, this n will be 0. So what will be the formula? QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. So simply if I use this formula, what I can work out? I can work out QR upon A without shield. So that I have worked out, I have divided it by 105. So this should be QR upon A with shield. Now we know the value of QR upon A with shield. Simply substitute this value 2.3864 over here. You know the value of sigma T1, T2, epsilon 1, epsilon 2, epsilon S. What is epsilon S? Epsilon S is the emissivity of the shield. So we know all these values. Only what is unknown? The unknown is N. In industry, in practical applications, we have to go like this. Being an engineer, we have to design how many shields should be there, what should be the emissivity of shields, what should be the spacing between the shields. Okay, is it clear to you? So if you go by this approach, you can work out number of shields. The number of shields will come out to be 3 point something, 3.98 something. So practically we cannot provide 3.98 shields, no? So we'll write that number of shields provided should be 4. Tell me very honestly, is it clear to you? We'll work out one more numerical and then we'll stop. Is it clear to you? So I will just revise what we have seen. We have seen the concept of surface resistance. We have seen the concept of shape resistance. What is surface resistance? Resistance offered at the surface to flow of heat for emission of radiant energy or absorption of radiant energy. It is 1 minus emissivity upon area into emissivity, right? Then we have seen the concept of shape resistance. It is 1 upon area into view factor or shape factor. 1 upon A into, let's say if the heat is flowing from 1 to 2, it is 1 upon A1 F12. Then we have seen electrical analogy, heat exchange between two plates, two infinite parallel plates when no shield was there. So what was the formula? QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by into bracket 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Right? Without shield. If one shield is there, then I will write plus one more term. The formula will be QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by, first bracket will be same, 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Plus in second bracket, it will be 2 upon epsilon 3 minus 1. If one more shield is there, let's say call it as plate number 4. So plus we have to add one more bracket, that is 2 upon epsilon 4 minus 1. Right? Okay, so we have worked out the numericals without shield, with one shield, with two shield, and in this numerical we have seen how to work out number of shields required, right? Now, in this numerical, in this formula, just look at the formula. If epsilon 1, epsilon 2 and epsilon s are same, I repeat, if epsilon 1, epsilon 2 and epsilon s are same, just take a special case that emissivity of the transmitting surface, emissivity of the receiving surface and emissivity of the shield is one and the same. So what will be this first bracket in the denominator? It will be 2 upon epsilon minus 1, right? Plus n into bracket 2 upon epsilon minus 1. So 2 upon epsilon minus 1, this bracket will be same, right? And what will be left in another bracket? It is n plus 1. So what is the simple formula? See, this is a special case. In practical, this case will not exist. It will never happen like you are using shield which is having same emissivity as that of the plates, right? Practically, we will use radiation shields having very low value of emissivities so that the surface resistances will be high and the radiant flux losses will get reduced drastically, substantially, right? But in competitive exams, this question has been asked that if emissivity of the plates and emissivity of the shields are same, what is the relation between Q with shield and Q without shield? So the relation is Q with shield is equal to Q without shield upon n plus 1. See, they will never ask you. Sometimes this formula is asked in the competitive exams, and sometimes a numerical is asked. For example, the numerical is like this. The heat transfer by radiation between two infinite parallel plates is 100 watts per meter square. It is decided to reduce the heat transfer by 10 times. If the emissivity of the shield and emissivity of both plates are same, find how many shields are required. Now in this case, what is Q with shield? Q with shield is 10. What is Q without shield? Q without shield is 100. So 10 is equal to 100 upon n plus 1. So n plus 1 will be equal to 10. So n will be equal to 9. Tell me very honestly, are you getting this? What is the formula? You have to remember the formulas. See, in GATE exam, nowadays it is objective exam, right? I have cleared GATE exam for 5 times with more than 95 percentile. See, it is not difficult, just you have to, and I was not that good in as far as manufacturing section is concerned, right? Being graduates, now you are in touch with material science also, you are in touch with manufacturing also. So if you are good in thermal design and manufacturing, you can clear GATE exam with a good percentile. And if you get good percentile, definitely there are bright chances that you will get absorbed in some of the PSUs. Some of the PSUs, if your GATE score is good, simply they will arrange your interview. They will not take written test. Simply they will take your interview and they will absorb you. If you are having a 2-digit GATE score, now one of my students in 3rd year, his GATE score was 99.98 something. His all India rank was 4, right? So if you get any 2-digit GATE score, GATE rank, right, you will get absorbed in any good PSU or whatever, like even if you want to do MTech, pursue MTech from IIT Powai in aerospace, you'll get admitted over there. Okay, anyway, what I mean to say that as far as competitive exams are concerned, your mindset should be conceptual. You have to look from conceptual perspective. If you want to score